I didn't say anything so far, so you've not lost anything. Nothing important. I must tell you that when I was asked for some reason to officiate and to act as master of ceremonies of this hopefully very important meeting of us, I just could not believe my luck. And the reason for this is that we are honoring people who have personally played some role in my own life and of course in the life of the country and science in general. And it is really a very important opportunity for me to say a few words about them. Let me tell you a little bit about Yuval, whom I think most of you know personally, and of course all of you know by reputation. Now, Yuval, I think, knew more about more things than most people in the world, for sure. And he had, I think, a memory that is very, very rare around people. And I would probably have needed his memory in order to memorize everything that I should have tell about him. So I just will use some of the items that appear in the paper that I have. Now, Yuval, of course, was active in a lot of field areas or activities, ranging from science, where he was basically a wunderkind, and then later became one of the leading scientists of his generation. He was active in the academic life of the country, especially in the academic life of Tel Aviv University at the beginning. He was responsible in many ways of making this what I hope is a good, maybe very good, hopefully excellent university. And certainly he was almost single-handedly responsible for constructing and building the physics department. I should also mention that his student, his first PhD student, was a #1 PhD degree awarded by Tel Aviv University. That person is unfortunately not with us anymore. He passed away a few years ago. That's Akiva Yaniv. He was a physicist. He was also active in politics, and in politics, I think, as well as in all other areas, he was always trying to conceive of what he thought best, to lead the way he thought people, institutions, organizations, countries should be led. And the same effort, the same thoughtfulness that he put into grand things, he also put into what not to him was small things, but less important things like people. And I must say that personally, when I finished my PhD at the Weizmann Institute or Hebrew University, it was Yuval who was instrumental in arranging the continuation of my career, as he was in fact doing for a number of people of that generation. I'm not sure if some of them are around here, but I'm sure that people who know us know who I mean. So he was, of course, awarded a number of honors, including the Israel Prize, Prize Emet, Prize Rothschild. But I think the most important honor for Yuval would be the generation and generations of physicists that he educated, inspired, and brought to flourish. Today we are beginning this afternoon by awarding the Yuval Ne'eman Chair in Physics, I think theoretical physics. The recipient is Professor Yaron Oz, the department chairman at the moment, and to present him and present the occasion, we have the honor of asking Professor Dani Leviatan, our rector, to say a few words.
Okay, good afternoon. Tzchak spoke about Yuval, and of course we all remember Yuval as a scientist, as university president, as the creator of the School of Physics here at Tel Aviv University, but also as a good friend. And I want to take the opportunity to thank Dvorah and the family for continuing relations with us after Yuval has gone. And for a few years we tried to get the archives of Yuval to Tel Aviv University, but somehow, for various reasons, Dvorah is already making faces, it did not work, and finally, luckily, the Minister of, the current Minister of Science took over and got the energy, Commission of Energy, of Atomic Energy, to take over the project, and I hope that the archives found a good home. I don't want to dwell too long. We are inaugurating the chair that was donated by Raymond and Beverly Sackler in the name, to be named after Yuval Ne'eman. And we decided already in 2008 that the first incumbent of the chair will be Yaron Oz, Professor Yaron Oz, but we have never gotten up until now to the opportunity to have the ceremony. So we are taking this opportunity, and I call Yaron over so that I can present to you the certificate, and I'll read the certificate. It is in Hebrew, so I apologize for those who don't understand Hebrew. וזאת לעדות כי ביום ראשון כ"ו באדר ב' תשס"ח 2 באפריל 2008 החליט הסנאט של אוניברסיטת תל אביב למנות את פרופסור ירון עוז מופקד הקתדרה על שם יובל נאמן בפיזיקה, עם כל החובות והזכויות הכרוכות בתפקיד זה. על החתום אני, בתור רקטור האוניברסיטה. אז ירון, זהו. תודה. אז אני רק אנצל עוד שנייה כדי לברך את המורה שלי, ישראל אומן, שייתן הרצאה היום. אנחנו מילאת את האולם, ג'וני. זה, אני לא יודע, אחר עוד כמה דקות. טוב, מי מדבר עכשיו? ירון אומר משהו? לא.
מישהו צריך לזכור את הסדר. פרופסור שמעון ינקלביץ' מהפיזיקה, רקטור לשעבר, חבר טוב. Professor Yankelevich, our pro-rector, a good friend of mine, and of course of many others, a physicist, will say some words about Yaron and about the field.
Dvorah, Teddy, the Ne'eman family, colleagues and friends. The ceremony today mixes sorrow and happiness. Sorrow because it reminds us once again of the loss of Professor Yuval Ne'eman, one of the really most outstanding scientists and scientific leaders that this country ever produced. If there is someone who merits the title of Mr. Science in Israel, it was and still is Yuval Ne'eman. Yuval, a brilliant scientist, an academic administrator and leader, a Renaissance man with a vision and ability to carry it through, a vision whose fruits benefit us all until today. We love him and miss him a lot as a scientist, a wise and thoughtful academic leader, a maverick person, a colleague, and a dear friend. Today's event is also a happy one. We celebrate the inauguration of the Yuval Ne'eman Chair in Physics with, as we heard, Professor Yaron Oz as the incumbent of the chair. As we heard, the chair was endued by Raymond and Beverly Sattler. Yuval was a very close friend of Raymond, who admired Yuval, and it was Yuval, to a large extent, who managed to attract and attach Raymond Sattler to the university at large and to our Faculty of Exact Sciences and the School of Physics. It gives me a special pleasure and pride to congratulate Yaron for this distinguished honor of being the incumbent of the Yuval Ne'eman Chair in Physics. I have to admit that talking of Yaron, I am totally biased, and I should add, rightfully so. So Yaron, you will have to endure through a few minutes of high praises, but as Adlai Stevenson said, praises will not hurt you as long as you do not inhale them. Yaron has been a superb PhD student of mine, the kind of student one is craving for and proud to have, a great colleague and scientific collaborator, and a real friend. Since 2006, as the head of the School of Physics, he is also my boss. So how can I have anything but the most sincere and objective praises for him? Our acquaintance actually started when one day back in 1990, he entered my office. If you think how young Yaron is and looks now, even after 4 years as the head of school, just imagine this young guy entering my office then, looking more like a high school kid than a PhD student. Yaron started his PhD at the Technion, but was interested in more theoretical aspects of particle physics. He had his own ideas concerning anomalies and anomalous theories, involving both gauge and gravity degrees of freedom, and looked for a supervisor to work with. I was lucky, and I do mean lucky, he came to me. Yaron was an innovative, creative, and independent student. From the outset, it was clear he's going to have an outstanding scientific career with major and distinctive scientific contributions. Indeed, in retrospect, this is certainly the case. A case I can proudly say, I told you so, but many people thought the same, so to whom I'm telling. We have heard of Yuval Ne'eman's and his remarkable achievements. It is almost impossible to compare Yuval to other Israeli scientists, physicists. Nevertheless, I would like to draw some parallel line between Yaron and Yuval. Just as Yuval, Yaron is a leading, worldwide acclaimed high-energy particle physics physicist. As Yuval, also Yaron shares a particularly strong knowledge of and love for mathematics, in particularly geometry, group theory, and algebraic topology, which allows him to talk on par with mathematicians. Much in the spirit of Yuval, Yaron keeps also a close eye at experiments and phenomenology, never forgetting that physics is an experimental science. Both Yuval and Yaron started their study at an early age, and did, some of them, at the Technion with distinction. Both served as physicists in the Israeli Defense Force, doing and supervising classified research, which contributed to the security of Israel. Both managed even during their demanding army service, to continue and produce forefront work in particle physics, a most difficult task. Both served, Yaron is still serving, as the head of the School of Physics. Yuval has established our School of Physics. Yaron is one of the most effective and successful head of school which we ever had, and I'm saying it as a previous head of the school. For Yaron, and here again following the legacy of Yuval, excellence is the leading factor. The School of Physics must recruit the best young physicists and provide them with the best infrastructure. The School of Physics must be the home to the best undergraduate and the best graduate students with all the financial support it entails. Yaron is fighting to achieve these goals under difficult budgetary cuts and constraints which endanger to undermine the physics program at our school, which must be the best, the strongest in the country. Yaron manages to do it skillfully, effectively, with determination and good spirit. It is amazing to witness that he can carry it all and still carry on with his leading and well-thought scientific work, devoting quality time to his numerous graduate students. Again, something Yuval was capable of doing. Just very few and short words about Yaron's academic career. Yaron, after finishing his PhD, served as a researcher in the Army between 1991 and 1996. During this period, he was a research associate at both Tel Aviv and the Weizmann Institute. He managed to carry successfully and effectively both the Army research work and the particle physics research work, a most difficult task that Yuval would have appreciated and admired. As a result, he managed to receive a postdoc at Berkeley and started to distinguish himself at the international arena with unique and important scientific work, some of which very highly cited. The next stage was a lucrative 5-year staff member position at CERN. Yaron could have easily stayed at CERN, but luckily for Israel and Tel Aviv University, he has decided to come back and join us. There is a famous saying, I think it's attributed to Vidal Sassoon, the hair stylist, that the only place where success precedes, come before work is in the dictionary. Yaron has put hard work to supplement his outstanding skills in physics, administration, and human relationship to achieve success in his various endeavors. I cannot think of anyone more deserving to be the incumbent of the Yuval Ne'eman Chair in Physics. Yaron, we have high regards for you and your achievements and wish you good luck and a lot of success in the years to come.
One of the most appropriate ways of honoring Yuval Ne'eman's memory is the awarding of a Fellowship of Excellence to a student for his research. The student is Dan Ben Yaakov. Where is he? Where is Dan? Oh, there he is. And I would ask Dvorah to award the certificate to him. It says, וזאת לתעודה על הענקת מלגת הצטיינות במחקר על שם פרופסור יובל נאמן לדן בן דב, חתום פרופסור ירון עוז, ראש בית הספר לפיזיקה ולאסטרונומיה. That was in Hebrew, what I said before in English. Okay. have now arrived at tzimuk sheba'uga, as they say, the topping on the cake, which is Professor Aumann's talk. I would not hold you long in telling about him. I was yesterday in a play called Ghetto, which many of you maybe have seen, and I cannot help but think about that particular play when I consider that Professor Aumann, I used to say Aumann. How do you say? Okay, Aumann. Yes. He was born in Frankfurt in Germany in 1930, and he left Germany I think in 1938, and so he had lived through some hard periods before he emigrated to the United States, where he studied at yeshiva and a high school, and then got a bachelor's degree at the City College of New York, and then a PhD in mathematics from MIT in 1955. In 1956, he joined the Hebrew University Mathematics Department in Jerusalem, and he stayed there ever since, of course, doing research in mathematics, in game theory, and getting a lot of awards even before he got the Nobel Prize in 2005. He raised, apart from a large family, unfortunately lost a son in the war in Lebanon, but he also raised quite a number of PhD students. We got the number was 16, and I think this is a source of pride to him. And he founded the Institute of Rationality, which combines people from all these disciplines at the Hebrew University. And I think he will talk to us about something which is really related to rationality. But I wanted to share with you one memory that I have of him. In 1956-57, when I was a first-year student at the Hebrew University, he was one of my instructors. Now, I forget what particular subject that was, but what I vividly remember, what I vividly remember is the playful way in which he hurled pieces of chalk to students who would not listen attentively to what he had to say. I don't know if you remember that, but I do. Okay. So now I call upon Professor Aumann to deliver his lecture. Okay. We have to do something with something.
Yeah. Okay,
put
let's try this.
Okay,
Yeah.
put this in your pocket.
How's this? Hello, hello? No. Okay. A little closer. Hello, hello, hello? Here's my memory. Good question. Hello? No. All right. Let's try this. However, the beard will interfere. Hello? How's that? No. Huh? The Beseder? The Beseder? Here's a memory stick. In the meantime, while we're waiting for the memory stick,
We need to put it a little higher.
It's here, it's here.
It might be on your color.
Okay. How's that? No good, huh? Better?
I think it's better.
All right. No, it's this one. Yeah. Let's go to...
You need help? Shall I send somebody?
No, I think...
I'm here, everything is okay.
Here, this. That's it, thank you.
1 minute.
Okay.
Yeah.
All right. Okay, fine. Thank you very much. So, honored Mrs. Neyman and family, children, children-in-law, rector of the university. By the way, Professor Yankelevich was characterized as the pro-rector. I'd like to say I'm not anti-rector. I'm pro-rector too. Okay. So I'm very honored to be here, and I'd like to start with a few words. Well, let me start with an anecdote about my first days in Israel. Yes, okay, which were mentioned that I threw chalk at the students. Yes, but here's another anecdote about that time. They gave me a class to start at 8:15. 8:15 in the morning, not in the evening. Yes, there was one mathematician, a famous mathematician in the United States, who was once asked to come to a seminar at 9 o'clock, and he said, "Well, I go to sleep late, but not that late." Yes. Okay. I was used to the wee hours of the morning, and an 8:15 class was not really for me, but it was a new job, and I felt that I have to live up to it. So the first class, I met them promptly at 8:15, and the next week also at 8:15, and the next week it was 8:16, and then it was 8:20, and then I settled down into a routine of showing up at class at 8:25. And a few weeks later, when I came in, there was written on the blackboard was in Hebrew, of course, "We don't understand why the honored assistant cannot arrive to class on time." I erased what was written on the board, and I gave the exercise, I gave the class, and the next week I arrived at 8:15. And there were 2 students in the class out of about 30, something like that, 2 students in the class. So I locked the door from the inside. And I gave the class to the 2 students. The next week, I was there at 8:15, and the whole class was there at 8:15, and I gave the class. The following week, I was there at 8:16. The week after that, 8:20. The week after that, 8:25. And there were no more writings on the blackboard. And we finished the term that way. So that's another anecdote of the chalk throwing era. Okay. Now we will get down to business. Yuval Neyman was really a giant of a man. Yes, I knew him personally, and not very well, but somewhat, and enough to realize that he was a true giant. Really unusual, I think, unusual as a scientist. Now, I think he had, I think, 4 major lives in one life. 4 major lives in one life. One was pure science. He identified the quark. He applied sophisticated, deep concepts of group theory and mathematics to understanding the structure of the atom, to understanding the structure of the particles, and he made tremendous strides in this. This is world-famous work. So he was an outstanding pure scientist. But he was also an outstanding applied scientist, okay? And he is largely responsible for the fact that we're still sitting here today, okay? Because he is largely responsible for Israel's atomic program, nuclear program, and he was the director of the Atomic Energy Center in Israel. I think, see, atomic nuclear weapons are there in order not to use them. That is their function. Now, that's my angle, okay? That's game theory. And I think a game theorist realizes, and everybody should realize, that nuclear weapons exist in order not to use them. The United States and the Soviet Union realized this in the long years of the Cold War. They served a very, very important function because they were not used. Yes, that was the function that they served. You know, I used to, well, I still do get to Cambridge, Massachusetts occasionally, and there were these disarmament drives which are ongoing for decades, yeah? And I saw a very nice bumper sticker on one of the cars in Cambridge that said, "One nuclear explosion could ruin your whole day." Yeah. So we want to avoid those nuclear explosions. We don't want to have our days ruined, right? And the way to avoid nuclear explosions is to have nuclear weapons. That's the way to avoid them. It sounds paradoxical, but that's God's honest truth. Now, that is not what I'm going to talk about today. I'd like to talk about Yuval, who was an outstanding pure scientist, B, an outstanding applied scientist, as I've just indicated, C, a outstanding academic leader, as we've heard all the time, and also D, an outstanding, how shall I say it? The word political, although I think politics is the essence of democracy, yes, but somehow the word political has gotten a negative connotation. It's not a negative connotation. Democracy is all about politics. That's what it's about. So, but I won't use this word, yes, because it'll be misunderstood. He was an outstanding public leader, an outstanding Zionist. Let me just quote from one of the things that he said in an interview, and it's maybe not politically correct to talk about Zionism nowadays, but he says as follows. In founding the Tchiyah movement, the Tchiyah, how does one say it in English? Rebirth. Revival. That's excellent. Revival. Dib is life. I sat with the people with the religious Zionists when we set up the Gush Emunim, for people who understand Hebrew, yes, religious Zionists, when we set up the revival movement, the revival party. And I say that our right to this country, our ownership of this country, follows from our history here. I depend on our historical our historical heritage and on the need to preserve the Jewish people, okay? And that is Yuval Ne'eman's Zionist leadership, public leadership. Now, I'd just like to add, before getting to the substance of my talk, I'd like to add that I got to know Professor Ne'eman personally, not very thoroughly, not very deeply. We weren't bosom friends, but I got to know him in carrying out one of his ideals, and that was in setting up the university center in Ariel, in the Judea and Samaria University Center. He was a member of the committee that brought this about, and at the first meeting of this committee, we were notified that the meeting has to be put off because Professor Ne'eman just passed away. So he was very active in this, and I appreciate his he had a lot of courage. Yes, he returned the Israel Prize when he was a recipient of the Israel Prize, and he returned it when it was granted to an Arab demagogue. So he had a lot of oomph, a lot of courage, a great scientist, a great pure scientist, a great applied scientist, a great builder of Israel academia, a giant of a man, and Chaval al da'avdin below mishtakrin. So now, what I'm going to try to sell to you today is the idea that pure and applied science are inseparable. In fact, there is no such thing. So the title of this lecture is Pure and Applied Science, yes. I'm going to try to sell to you the idea that there's no such thing as pure and applied science. What there is science, okay? Now, in science, science is motivated by applications. Science is motivated by questions of the real world. That's what motivates science, okay? So, there's no such thing as pure science because it comes from applied science, okay? But also applied science comes from pure science, also the other way around. Without the pure science, you cannot have applied science. I just came back from a week in China a few days ago, and China is an amazing country. The way it is leaping forward economically is truly amazing. But what they are lacking is sufficient emphasis on pure science. And then I've told them that they're not going to get forward until they say, hey, let's just satisfy our curiosity. Let's just go where our explorations lead us. Never mind what the applications are. They will come by themselves. Without having an idea of pure science, you will never be able to do good applications. And what I would like to do today is to illustrate this by means of my own career, my own researches, okay? And not only researches, but my own studies. I'm going to go back to my undergraduate days at City College of New York. I became fascinated by the study of number theory. Now, what is it that fascinated me about number theory? Four things. First of all, the questions are very natural. They're natural questions. And we'll get to, I'll give an example in a moment. But before giving the example, I want to tell you, the questions that are asked in number theory are very natural, simple questions, questions that suggest themselves. Second of all, they are very easy to formulate. The formulation of the question, a school child can understand the questions. And maybe we have some school children in the room. We'll try it out in a moment, okay? The third point is that the answers are very, very difficult, very deep. You cannot do, in much of number theory, not in all of it, but in much of number theory, it's very difficult to prove anything at all, okay? And the fourth, and in my mind over there in the late 40s in New York City, was that it is absolutely useless, okay? Absolutely useless. Now, there was a great mathematician by the name of G.H. Hardy, yes, and he was perhaps the top number theorist in the world in the first half of the 20th century. And the matter of being useless, of not being applied, yes, was a sort of a cult, okay? It was very important not to be applied, yes. Now, Hardy had once done some work in genetics, and he said later on in his life, in mathematical genetics, later on in his life, he said, the only thing I regret is having done something which appears to have some use, yes? So that's what he regrets. And I was a young and impressionable guy, and this cult sort of caught me up. So I decided to read number theory. And I became very involved in number theory. And let me give you an example of number theory. It's a famous example. Let me see how this works. Here we go. Number theory. Fermat's theorem. Now, some of you may know this. I beg them for indulgence while I go a little bit into the rest of into this matter for the benefit of those who don't know about it yet. So, the Egyptians, the way that they constructed a right angle was to take a triangle with sides of 3, 4, and 5, and a triangle with sides of 3, 4, and 5 must, the bottom angle there must be a right angle, 90 degrees, must be, okay? That's Euclidean geometry. Some of you may remember that from your high school days. And the essential characteristic of this, how do we know that you get a right angle, is because of the theorem of Pythagoras, which says that 3 squared plus 4 squared equals 5 squared. 3 squared is 9, 4 squared is 16, and 5 squared is 25. 9 plus 16 is 25. The moment you have that, you know that you have a right angle there at the bottom. Up to now, I said that to prove anything, you need some very, very deep thought. We haven't gotten to the deep thought yet, okay? So don't think that this is deep for Oman, yes? Okay. Now, a natural question to ask is there any other way that you can construct a right angle? Are there other pairs or triples of numbers, x, y, and z, with the property that x squared plus y squared equals z squared? So if you take a triangle like that, x, y, and z, of course we're not talking about multiples of 3, 4, and 5, we're talking about other things. So I think it's 5 squared plus 12 squared equals 13 squared. So that is another triple like that. And there are many more. There are many more. Okay? So now the next question to ask is, here we have 3 squared plus 4 squared equals 5 squared. And now we ask, well, what about if you don't limit yourself to squares, but you talk about cubes? Are there any numbers x, y, and z for which x cubed plus y cubed equals z cubed? So this is already a lot more difficult, but it turned out that there are no such numbers. And then the next question was, what about x to the 4th? I mean, you can keep many generations of mathematicians busy with this, and they can make a living for many generations, for many years, if we take them one by one. So the next item was, what about, is there, for any exponent, n, is it possible to have x to the n plus y to the n equals z to the n? Okay? Now, when I was a student at university, at City College in New York, the answer to that question was not known. They had gotten up to exponents of 687, and that was the largest exponent for which they knew the answer, and the answer was always no. Always, always no. It's impossible. Then during the years, they started using computers and deeper methods, and they came to the conclusion that up until about 2000, the answer is no. But the question remained open, is there any number n for which x to the n plus y to the n equals z to the n, for n greater than 2? Integers x, y, and z, such that x to the n plus y to the n equals z to the n. Now, this is a problem which is very, very old. This problem is 350 years old. It was formulated by a French mathematician by the name of Fermat, who claimed that he knew how to prove that the answer is no, but his proof was not preserved, and the problem started fascinating mathematicians in the middle of the 19th century, and through almost the entire 20th century, nobody could do anything with it. And finally, I think it was in 1994 or something like that, the problem was solved by a British mathematician at Princeton University, Andrew Wiles, who showed that indeed it is impossible for any number n larger than 2 to solve this equation. Now this is very, very simple to formulate. I hope I have not lost any part of the audience. It's very, very simple to formulate. It's a natural question. And the answer is extremely, very, very, very deep. I don't get close to understanding the answer, yes? By the time it was published, it was much too late for me to understand that kind of mathematics, yes? So it is very, very deep. And this kind of thing, there are other problems in number theory that fascinated me as an undergraduate, and I read a lot of them because of those 4 factors. Now, what are you going to do with it? All right, so x, y, z, n, it's impossible. So what? Yeah? What are you going to do with it? Yeah? It really sounds absolutely useless. But it need not be absolutely useless. I don't know of an application of that very result, but results that were considered totally useless about the distribution of prime numbers, which I read a lot of when I was an undergraduate, have suddenly turned out to be very, very useful. They are useful. A proper understanding of prime numbers is essential in cryptography, yes. You wouldn't be able to use your computer without number theory, yes, and fairly deep number theory. You would not be able to use your computer without it. I'm not able to use my computer even with it, but the rest of you wouldn't be able to use your computer without it because the hackers would totally destroy it. You need cryptography, and cryptography nowadays depends heavily on the theory of prime numbers, and so an understanding of that was there because of people like Hardy, okay, who had created, you know, they would turn over in their graves if they knew that their stuff was being applied, okay? So there's no difference between pure and applied science. And now, when I went to graduate school at MIT, I studied topology, algebraic topology, point set topology, from well, my teacher was George Whitehead, and topology fascinated me, and especially one aspect of topology fascinated me, and that is knot theory. Okay? Now, what fascinated me about knot theory is those same four factors. Remember, this is only a few years after finishing City College, okay? So I was still under the spell of this cult of anything that could be applied is filthy, okay? What attracted me to in topology in general, and not so much topology in general, but the knot theory, was those same four factors. And those four factors were, if I may recall, one, the questions are very natural. Number two, they are very easy to formulate. A school child can understand them. Number three, it is very difficult to prove anything, and I may say even more difficult in knot theory than in number theory. We have some things that are fairly easy to prove. In knot theory, there isn't anything that's fairly easy to prove, okay? Everything there is very deep. And number four, it was absolutely useless. Now, I'll give you an example. I'll give you a very short introduction to knot theory. I'll try to give you a taste of what it's about, and afterwards we'll talk about pure and applied science. You see over here we have four knots, okay? So the way when we tie a knot in a string and we splice the two ends of the string together in order to get a circle, otherwise any two knots are equivalent. But we ask each other, for example, the two knots on the top, they're both versions of the granny knot, the simplest knot there is, the red and the blue. But there's a difference between the red and the blue. They look almost the same, but they're different. How are they different? Where there's an overcrossing in the red knot, there's an undercrossing in the blue knot, right? So now we ask ourselves, as we always do in knot theory, without cutting the rope, can we transform the red knot into the blue knot? Okay? Is there some way of manipulating the red knot into the blue knot? And we have the same thing on the second line. We have the same question. We have there, this is not the granny knot, it's a different knot. But over there also, the green and the purple knots differ only in that where the green knot has an overcrossing, the purple knot has an undercrossing, right? So can we transform the green knot into the purple knot without cutting the rope, just by sort of fooling around with your hands? we have two questions for two knots. Now, in fact, the answer to the second question is yes, we can. The green knot can be transformed into the purple knot, and the purple knot can be transformed back into the green knot, and that's not something which is very difficult to prove, because you just do it, okay? You just take the rope, you splice, you put the knot into it, you splice the ends together, and then you do a transformation with your hands, and I leave it as a challenge to the audience, whoever is interested, actually to take a piece of rope and to try to do that. It's not trivial, but it's not very difficult, okay? But don't try to do it in your minds now, because I want you to continue to listen to my talk, okay? All right, so it is possible to do that on the bottom there, yes? It is possible to transform the green and the purple knots one into the other. But it is impossible to transform the red into the blue or the blue into the red. That is impossible. Now, how do you prove that something is impossible? To prove that something is possible, you do it. How do you prove that something is impossible? Well, huh? You don't do it. Unfortunately, that isn't enough to prove that it's impossible, but this is a result of considerable depth. Here already you need quite deep methods of algebraic topology to prove that, but this is a known result. Now, incidentally, these knots are called alternating knots. Why are they called alternating? All four of them are alternating knots. Why are they called alternating knots? Because as you follow along, if you look at this as a road, yes, sort of a closed road. How you get on the road isn't clear, but let's say you climb on the road, you climb over the fence, it's a closed road, and as you walk along the road, you go on an underpass, and then the next one is an overpass, and then the next one is an underpass, and then the next one is an overpass. So it alternates between overpasses and underpasses, okay? So a knot in which the overpasses and the underpasses alternate, that is called an alternating knot. All right? By the way, I just want to say that this question, whether the blue and the red knot can be transformed one into the other, or for that matter, the purple and the green, these are questions, I think, that you will agree with me. These are natural questions, okay? It's even more natural than x cubed plus y cubed equals z cubed. And they are, moreover, you can explain it to a school child. The school child will understand what you mean whether you can transform one into the other. And as I said, it's very difficult to prove anything about them. And as I thought at the time, these things are absolutely useless. Now here are some examples of alternating knots which are made up out of more than one piece of rope. Here you have two pieces of rope, okay? You see on the top line, you going from the top, you have the purple knot going over the green, and then under the green, and then over the green, and then under the green, okay? So it's an alternating knot. Also the green one, it goes from the top, it goes under, over, under, over. So you have an alternating knot over there. The bottom is even simpler, okay? You have the blue one going over the red on the top and then under the red. And the red one going under the blue and then over the blue. These are alternating knots made up out of more than one piece of rope. Now, there's there is an interesting fact about these knots, and that is that they will not come apart. Okay? Without cutting the rope, you can't pull them apart. This is intuitively obvious, but to prove something like that, again, this is an impossibility result, okay? When you can do something, then you just go ahead and do it. When you can't do something, then it's quite difficult to prove. It's like trisecting an angle or doubling a cube. To prove that those things are impossible is quite difficult. Here also, to prove that these things cannot be pulled apart is quite difficult. Now, let's take a look at these two knots. First, let's take a look at the bottom one. The bottom one is not an alternating knot. Look on the left side of the blue knot. It goes over the red one, and then again over. And then it goes under, over, and then again over, and then under, and then over. Okay, that's the blue. So this is not an alternating knot. Okay? It's not alternating. And indeed, if you just look at it carefully, you can see that it can easily come apart. Okay? You can easily take it apart. What about the top one? The top one is the famous Ballantine rings, or that's if you drink beer, and they are known since ancient times. It's called the Borromean rings. The Greeks knew it as the Borromean rings. These here, this is a very special knot that's made up out of 3 components, and you see that any two are not connected with each other. The red one lies entirely above the blue one. It lies entirely under the green one, and the green one lies under the blue one. Okay? So the red lies over the blue lies over the green lies over the red. Okay, this is a circle, yeah? Any two are disconnected. All 3 together are, as it happens, are inseparable. You cannot pull this apart. How do we know that you cannot pull it apart? The reason that we know that you can't pull it apart is because of a theorem. Alternating knots don't come apart. Okay? Now this is a theorem which, again, I would like to emphasize, it's a very natural theorem to wonder about. Any school child can be explained this theorem, and believe me, it is very, very difficult to prove. And the reason you should believe me is because I did this for my doctoral thesis, yes. I was the first to publish a proof of this for my doctoral thesis, that alternating knots do not come apart. Now so it follows that the Borromean rings will not come apart. All the other alternating knots that we showed will not come apart. And I thought that that was a nice achievement, and in fact, I was given a doctoral degree for this, okay? All right. The basic idea for this, the last difficulty in proving this was overcome while I was standing in the shower in my room, and I was standing there wasting a lot of water. My wife, Batya, is very angry at me that I still nowadays spend about half an hour in the shower, and it wastes the water of the state, but that's where I get my ideas, okay? So I got the final idea for this and standing in the shower one day in October of 1954. I don't remember the exact date, but I do know that it was in October of 1954. In October of 2004, so almost exactly to the day, 50 years later, half a century later, the phone in my flat rings, about 10 p.m. On the line is my grandson, Yaakov Rosen. He says, Saba, Grandpa, could you explain to me what linking numbers are? I say, linking numbers? Like in knot theory? He says, yes. Like in knot theory. So I say to him, Yaakov, you're in the second year of medical school at Beersheba. Why are you interested in knot theory? So he says, Saba, we're learning about knot theory in medical school, and my professor started talking about linking numbers, and I don't understand what he said, and I don't think he understood it either. I said, why are you studying knot theory in medical school? So he said, well, sometimes the DNA in its cell gets knotted up, and depending on the linking numbers, on the characteristics of the knot, this could lead to trouble, or it could be totally innocent. I was totally bowled over. I had to sit down. Here, this stuff that I had been doing 50 years before, with the hope, with the idea that this is absolutely useless, yes, is now being taught in the second year of medical school at Beersheba. No, it totally blew my mind. But you know, it wasn't too bad, because by that time I'd been in applied mathematics for more than 40 years already. So I just want to say it in English, I consoled myself with that idea that in addition to number theory, which had become highly applied already 30 years before, now knot theory, what I had been doing for my thesis 50 years before, was also highly applied, was being used in medical school to cure people, to save their lives. So, I don't know, I hope that I have conveyed to you the message that I wanted to convey to you. There's no difference between pure and applied science. You need both. They feed each other. Applied science gives you the motivation, gives you the ideas, gives you the direction to explore in pure science. And pure science, when you explore something to the end, eventually it becomes highly useful. If the ideas are important enough, if they're beautiful enough, I might say, yes. I mean, this Wednesday, when is Shavuos? On Tuesday? No, on Wednesday. On Thursday, I'm giving a talk about aesthetics and science, beautiful proofs at Bar Ilan University. So the beauty of a scientific idea is, I think, a good measure of its eventual usefulness. If it captures your imagination, then it's going to be eventually useful. So what I try to sell to you today is the idea there's no difference between pure and applied science. And those people who try to say, let's get off the pure science and let's put our money and the money of the state into applied science, into things that are really useful, they're really missing the boat. And I think that is a a part of the message that we can learn from Yuval Ne'eman's life. Thank you very much. Questions?
Questions or compliments?
Oh, okay. All right, we'll start here. Okay. Okay, thank you.
Well, are there any remarks? I want to make a remark about number theory. And there are two things. First of all, you can take a number as high as you like. You add 1 to it, and it's completely different. So that's one thing. And the other thing I read as a young pupil, a problem, what is the largest non-prime number? And that sounds crazy, but the question is, what is the largest non-prime number that you know you can prove is non-prime without knowing any of its divisors? So that was really another one of these examples. A simple question and a very complicated answer. I would like to thank, in the name of all of us, Professor Aumann for this very, very important and elucidating talk. We could have gone forever listening to you, I must say, and I'm sure we'll have other opportunities. And I would like to thank the audience for coming to the Yuval Ne'eman Memorial Lecture, to recipients of the awards, and to the family, of course. Thank you.